Welcome everybody to the summer semester. We have a packed 90-minute lecture today, so that's why I started already here. First, let's resynchronize. Where are we? We're doing cryptography here, right? Intro cryptography, second semester. What we did so far in the first semester, we did in particular symmetric algorithm, DES, triple DES, AES, modes of operation, blah, 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 blah. And then we started the last couple of weeks or so, we started with asymmetric cryptography or public key cryptography. And what we did so far, the last 2 weeks, where we talked about RSA. It turns out, and I don't think I've told you that, in the world of symmetric algorithms, there are a million different algorithms. Not a million, but hundreds. Literally, there are hundreds and hundreds of block ciphers and stream ciphers. The world is entirely different in the world of asymmetric cryptography. There are essentially only 3 families of public key cryptography that is at least that's being used in the wild, that meaning in your web browser, right, or your smartphone. Who has a web browser? Okay, very good. So you have either A, B, or C on board, right? And most of them actually have all 3 on board. We did RSA so far. The second big family of public key algorithm belongs to discrete logarithm. Discrete log, you have no idea what that means. We're going to do that today. Right? Towards the end of the lecture, you'll know hopefully what discrete log is, and then next week we going to do a lot of things with discrete logarithms. So today we start with this, and I think we're going to spend 2 or 3 weeks here, and then we're doing elliptic curves, which is somewhat the high point of the course, I hope. So, program today is we do something really, really cool and motivational, which only takes us 5 minutes, and it's to some extent the coolest scheme in this 2-semester course. So please stay awake the next 6 minutes, okay? And then you shouldn't go to sleep, but this is really cool. And then we do essentially 80 minutes of hard mathematics, middle hard mathematics. We talk about finite groups and cyclic groups, which are the mathematical structure that we need in order to build discrete logarithm system. But first, I'm going to show you what the beautiful things that you can do with discrete logarithm, namely Diffie-Hellman key exchange. Okay, so the first chapter, kleines Kapitelchen, will be Diffie-Hellman key exchange. It's super surprising, really verblüffend, right? Flabbergasting, and really cool, and super simple, that's the thing. So, where are we? You've seen this picture, right? Who doesn't remember the system? This picture should unenroll, right? Drop out, study Germanistic or something. This is very important, okay? This is symmetric key cryptography. What is the old problem here? What do I have to do in order to realize this picture here in practice here? What is prerequisites? And you can answer in German if you want. Was muss ich hier machen? Yeah. Schlüsselaustausch. You have to exchange keys, right? And I just write key here, but in practice, who's going to do that? Well, and there's this marvelous scheme by Whitfield, Diffie, and Martin Hellman, and we're going to see that now. That's the Diffie-Hellman key exchange. So now I'm going to show you a really cool trick how Alice and Bob can agree on a key by just exchanging stuff, messages over the channel, and this stays unsecure. Meaning Oscar can still read. Oscar can read everything that's is going over the channel, and still only Alice and Bob can compute a secret key. We have Alice and Bob. What we do need are a set of public parameters Public parameters means this is a set of numbers which are just known to everybody. They're also sometimes called domain parameters. This is P a prime, and alpha is just an integer. And we're going to talk much more about alpha today and next week, okay? But they're publicly known. Now Alice generates her private key, which is lowercase a, which is private key Alice. And because it's a real pain to write this long thing here, we just call that lowercase a. which is a random number from the set 2, 3 up to p minus 2. It's completely symmetric, that protocol. That means Bob does exactly the same. Bob computes his private key Bob, which is denoted by lowercase b, which is taken randomly from the same set of integers, 2, 3 up to p minus 1. Again, p is a number, a prime number, and it's similar to RSA. Talk about large numbers, 1024 bits or much longer. I'm too fast. Sorry here. So now Alice computes her public key. You know, in public key cryptography, you have a private key and a public key. So Alice computes her public key, uppercase A, which is simply A, which is alpha, this public element, everybody knows alpha, raised to the 8th power, and A is her private key, mod P, which is Alice's public key, and she can send that public key over. It's a channel. Bob does the same. Bob computes B, which is alpha to the lowercase b, mod P, which constitutes his public key. So what does Bob do with his public key? Well, he makes it public, right? And we can visualize that by saying, okay, he's sending that actively over the channel. Alice and Bob exchange keys, and that's why it's called, yes, that's one reason why it's called Diffie-Hellman key exchange. So what happens next? So far was very simple, right? Alice did one exponentiation. Now she receives the public key of Bob. What she does is she does another exponentiation, namely with Bob's key. That means she takes this public key of Bob and raises that again to the 8th power, modulo P. You saw I left a little bit of space here, right? It's a little pedagogical trick of mine. So, and Bob does the same. So Bob takes the public key he received from Alice, and again takes this to his B power, modulo P. And now the surprising thing is what they compute, both Alice and Bob, is the same value. And we may want to call this KAB, which is the equivalent sign here. So this is KAB. Meaning we are done with the key exchange. Are you stunned? Are you flabbergasted? Haut das Sie No, okay, it's maybe too early. So I think this is super cool. Okay, so this is end of key exchange. And I'm going to talk a few more minutes about that, just to give you a little bit more feeling. So what can we do now? Well, for instance, you can use this KAB to AES encrypt stuff. So let's say you want to encrypt X. X is really long. That's your illegally downloaded Hollywood movie, right? You would like to encrypt that before you share that with your best friend or girlfriend. So and they're using AES because AES is very, very fast with encryption. So you want to AES encrypt that, and now you can use this KAB here as the encryption key. You get your ciphertext Y. Y goes over the channel. And on the receiving side, Bob, of course, wants to decrypt AES to the minus 1 power. And again, they both know the same key here, so he can again use KAB to decrypt. Okay, so that's key exchange. Yeah, and this is make use of the key. And this is just one example. You can do many other things with a shared secret, with a shared key. Okay. We're going to talk much more about Diffie-Hellman next week. Okay. The only thing I want to show you now is I want to give you proof of correctness. What is that? I want to show you why is that working. Does anyone here have a rough idea why b to the a and a to the b's end up being the same number? Does anyone have an idea? Yeah? Yeah? All exponentiation. And it's very simple. It's like 7th grade math. Ja? Siebte Schuljahr. Exponentialgesetz. It's very simple. What Alice computes she does b to the a here, right? So she does. But where is b coming from? Well, b was generated by Bob. This is Bob's public key, which is alpha to the b to the a. And this is alpha to the ab mod p, okay? Now let's see what this is here, right? Now let's see how which computation Bob does. Bob computes uppercase to the b and uppercase a, Alice's public key, public, was computed as alpha to the lowercase a to the b, and this is, surprise, surprise, alpha ab modulo p. Isn't that cool? And this is one of the things you have to learn by heart, meaning auswendig lernen, okay? If I'm going to call you in July and there's a final exam coming up, you have to know that if I call you at 3 a.m. in the morning, okay? This protocol, this correctness proof, very important, very fundamental, super cool. It's being used all the time in every web browser on planet Earth, more or less. Super important. So, this is kind of a motivational thing. There will be some homework problems dealing with Diffie Hellman, and now we're doing kind of the underlying math, and towards the end of the lecture, in particular next week, you will understand kind of the deeper mathematics behind that. You know, what is, for instance, what is alpha? Okay. So, but now, for now, we are done with Diffie-Hellman key exchange. Okay. Again, just remember, Professor Parr showed us something really, really cool that's important. Okay. Now we're going to do math. Chapter 2 deals with finite groups. What a group very roughly is, engineering definition, okay? A group is roughly set with elements and one group operation. Meaning, you know, sometimes that helps a little bit. You have some kind of cloud which could be finite. So these are a cloud of elements. So you have an ensemble, a set, eine Menge of elements. This is the group G here. And you can somehow compute in that group. Computing, meaning you have an element A and an element B, and you can somehow do, I call that A circle B, A donut B, A kringel B, okay? Which can, in practices, we usually call that plus or times, right? Plus oder mal. But so this is a basic idea. And this is a little bit too hand-waving, even for us. Hand-waving means too ungenau. So we have to look at a little bit more details. Namely, The exact definition is the real definition is, of course, definition 8.2.1 in our textbook, Understanding Cryptography. Or the other thing, the new people that are new in the class here, you can get that book at a really good price from us. half price, so Springer really is nice to us. So, was ist 821? Definition 821, definition 8.2.1 is the thing that you see up there. And I don't want to walk you through all of that, but maybe I'm going to talk briefly about the most important aspects. In short, in Kürze, zusammengefasst, what does this? We have 5 properties of groups. We have closeness, which means in German Abgeschlossenheit, right? Which is like if you have A and B coming from the group, from G, then the result of your group operation of donut, right? Of circle, of kringel. The result of that operation is C, and surprise, surprise, this is also in the group. Means the result is here and not here, right? Abgeschlossenheit. Associativity. Associativity. Meaning, if you perform the group operation multiple times, A plus B plus C, or A times B times C, it doesn't matter, the sequence doesn't matter whether you do first A plus B, or if you do B plus C or times C first. Now it's getting a little bit more interesting for our purposes here, for cryptographic purposes. There is a neutral element such that, so does, A times, or A donut 1 is equal to what? What is the definition of the neutral element? What is the result of that? It's A again, right? It's neutral, neutral, right? It doesn't change the A element. And this is really bad notation here, right? The clear stuff is up there, right? With, for all A, blah, 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 blah. So this is just a summary for engineers. Now maybe the fourth is maybe the most important property for us here. There are inverse elements. That means every element A of G from the group has an inverse element. That means for a given A, there's an inverse element, and if we have a multiplicative notation, that means donut means times mal, we denote that by 2 to the minus 1, right? We're used to that. So, how is that defined? Element times its inverse element must be what? Which number? Yeah, 1. Where is this 1 coming from? This is not necessarily the one you know from elementary school, from Grundschule. Where is this 1 coming from? This is this one here, right? So this refers to the neutral element, property 3. Right now I say, yeah, but it's the 1. And then today it will be the 1, but if we do elliptic curves, right? You remember I mentioned elliptic curves, which we do in 3 or 4 weeks, is something really wild. Point at infinity, right? This is not the one you know from Grundschule, okay? So, and then there's the fifth property, commutative commutativity, I guess, if you want to have proper nouns, which says if we do A times B, we might as well do B times A, which is kind of an additional property. So, property 1, 2, 3, and 4 must hold for all groups. So all groups must fulfill those 4 properties. If they don't fulfill them, you don't have a group. If the group also happens to be commutative, then this is called an abelian group, after Abel, which was a Danish mathematician. So far, so good. And now we're going to play with that. So we do an experiment. Is Z9, Z9, I'm going to recall in a minute what that is, we had that with RSA, is Z9 together with the operation multiplication, so this is donut here, right? This is donut, a group. Let's first recall what Z9 is. Z9 or Z9 is this ensemble of integers 0, 1, 2, 3, 4, 5, 6, 7, 8. This is the set. Remember, group, I told you, engineering definition, set with elements. I just showed you the set. And a group operation, well, it's called times. It's a little bit more. Donut is multiplication modulo 9. And we spend a lot of time in the winter semester talking about modular arithmetic in this integer thing, right? Integering. Okay, so what you now really have to do, and we don't have time, is we have to go through all these 4 properties and show whether these 4 properties are really fulfilled for this structure here, right? For instance, closeness, Abgeschlossenheit. That means if we multiply 2 elements, modulo 9 that is the result really in this set here? What is your gut feeling, yes or no? Yeah, of course, right? That's why. Yeah, of course. That's one of the reasons we do modulo 9 arithmetic. So closeness is fulfilled, associativity is fulfilled. Neutral element is a problem, but what is the biggest problem here? Do you remember? Which thing is not fulfilled? And we talked about it, I think lecture 2 in October. Which is the problem with if you do modular arithmetic? Which thing? Yeah, oben. Yeah, the inverse element doesn't exist for all. That means not all of these, some of these have inverses, some don't. Okay? The problem inverses only exist for elements A which fulfill what? What is the requirement so that an inverse exists? Yeah. Deutsch oder Englisch? Yeah. Yeah, GCD of this element. And? Very good, and it's a 9, excellent. Must be what? The GGT, the GCD must be which number? 1, very good, relatively prime, okay. So, turns out we have some troublemaker in our set, right? For instance, what is the GCD of 0,9? What is the GGT for 0 and 9? Na, ich sehe große Kinderaugen hier. 0 is wrong, 0 is wrong. 9, okay, 9. So 0 doesn't have an inverse. What about 1? Yeah. What about GCD 2 and 9? What is the GCD? 1 is fine. What about 3? GCD of 3 and 9 is 3, so that doesn't have an inverse. GCD of 4 and 9? 1. 5 is a prime, it's easy. What about 6? 6 and 9 is the GCD is 3 again, so 6 doesn't have an inverse. 7 has an inverse, 8 has an inverse. Okay? That means those yellow underlined numbers have inverses. 0, 3, and 6 are troublemakers, right? They refuse to have inverses, and there's nothing we can do about it. And now we do something really sneaky. We define a new group, Z9, and we kick the troublemakers out. 0, 3 und 6, 0, 3 and 6, and we call that Z9 star, which is Z9 without the elements that don't have inverses. That means we get this new set, which has 1, 2, 3 is kicked out, 4, 5, 6 is kicked out, 7 and 8. It turns out this Z9 is a multiplicative group. Which is just looking up. I think I'm almost certain it's in the book. Yeah, which is theorem 8.2.1 in our textbook. This is definition 821, but there's also a theorem which is coming up somewhere here. I have to be a little bit smaller. Okay, so you see here the set Zn star, which consists of all integers blah blah blah, for which this GCD condition is fulfilled, forms an abelian group under multiplication. Let's maybe talk a little bit about it. So one thing that we stumbled upon before with this, the plane Z9, was that not all elements have inverses. What about here? Do you think all elements have inverses? Yeah, right, we kicked them out. So here's maybe a thing that's now a little bit surprising, which is property 1, which is this closeness, Abgeschlossenheit. Right? I mean, in this case, that was more or less trivial, right? That it's abgeschlossen. What we do now, we kick 3 elements out, and suddenly, the theorem tells us it's still closed, it's still abgeschlossen. And why is that surprising? Well, it could happen, that you multiply 4 times 5 modulo 9, and the result is 6, for instance, right? You know what I'm saying? And then it wouldn't be abgeschlossen, it wouldn't be closed, because the 6 is not part of this element, of the set anymore. But you don't have to worry. This theorem tells us this is a group, meaning if this is a group, it's of course also closed. It means property 1, 2, 3, 4, and actually 5, because it's an abelian group, is also given. This is given in the theorem. If you do that, it will be very important. We like these groups. Now there is a note. Z star almost always in discrete logarithm systems I'm tempted to say always. We're dealing always with a star kind of thing, Z star, and almost always we don't have 9 here, or 8, or 100, but a prime number, okay? Z star P is prime, forms a multiplicative group as follows. The question is, if you do so now we're talking about groups with the element 0, 1, 2, 3, blah, 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 up to p minus 1. P being prime. And now what you're checking for is GCD A and P, whether they're relatively prime. And for which elements is that fulfilled? Pretty much all elements, because P is a prime, right? It doesn't have divisor, it doesn't have titer here. With one exception. Which of the numbers 0, 1, 2, 3 up to p minus 1 is not relatively prime to p here? Yeah. 0. You have to kick the 0 out, and that's the only one you have to kick out. That means 0 star, 0 p star, so Prim Gruppen always start with the 1 and then have all integers included up to p minus 1. Okay? Very, very, very important. Not difficult, just important. Important for your web browser. So, this was a little bit very brief, very dirty, unmathematical introduction to groups, to finite groups. And now we come to the high point of the lecture, namely cyclic groups. So now we're going to look at properties of these kind of groups, and there's some things that happen are very, very surprising stuff you probably have never dealt with, never thought about, because you never needed it. So that's chapter 3 for today. Cyclic groups. Okay, we start with the with a finite group which is eine endliche Gruppe, and this is exactly, I'm not writing that down. I mean, this is exactly the definition you would expect. You know, if I ask you, when is a group finite? Well, probably if we have a finite number of elements, eine endliche Anzahl Elemente, right? For instance, the reals, right? Die reellen Zahlen, the real numbers are not finite because they're infinitely many, right? Or the integers, there are many, many integers, so this is not a finite set, this is an infinite set. But when we call a group finite, a group G with the element donut, right, with Kringel, is finite if it has a finite number of elements. Very complicated. No, not very complicated, very trivial, yeah, right? I was almost embarrassed to write that down as a definition here, okay? So this is very trivial. The only thing which is more like a Vereinbarung agreement, we call the number of elements number of elements of G is equal to the, it's also called the cardinality of G. This means how many elements are in this group is also called the order of G, and the shorthand nice mathematical notation for that is, you know, this group G with bars, mit Strichen links und rechts, right, left and right bars. For instance, what is the cardinality? What is the order of Z9 star? That means how many elements are in this group? Well, you have to look there. 1, 2, 4, 5, 7, 8. So the cardinality is 6 here. Very difficult. No, not very difficult. Very easy. But this is just warming up, okay? Now it's getting, so now actually what the next, whatever, 20 minutes or so, the most important part of this lecture today. Let's do an experiment. Experiment number 2 for today. We consider, first we need a group, so we need the star symbol, and we want to have this with a prime, with modulus prime, so let's pick 11. This is nice for doing examples. 11 is a prime. Which elements are in this group? Well, the elements 0 is kicked out, but then 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 are the group elements. And now I pose, we do a crazy experiment, right, without any Sinn und Verstand, right, without any, you know, rationale behind it. We do a crazy thing. We ask ourselves, what happens if we compute all powers of a equals to 3. Okay? Powers sind Hochzahlen, ja? A hoch 1, A hoch 2, A hoch 3. Why? Well, I told you, it's a crazy idea, right? Because I'm your father, right? Weil ich das sage, okay. So let's look at a to the 1 is 3, right? A to the 2 is 9, okay, still okay. A cube, a to the 3rd, or a cube, is 9 mal 3 is 27, but you have to, it's 27, but you have to modulo, of course, we're in, you know, Z11, so you have to reduce modulo 11. And what's the remainder here? If you divide by 11, what's the rest? 5, very good. Okay, let's continue. A to the 4, which we know is a to the 3 times a, so this is 5 times 3. So this is just a shortcut computing here, right? So otherwise you, a to the 4, 3 to the 4 is 81, and then it's getting really hard with the mental arithmetic, but here this is easier. 5 mal 3 is 15, right? 4 times 3 is 15. Modulo 11 is 4, very good. 4 is the result. Okay, let's continue. It's so exciting. It's a little exciting. So, a to the 4 times a. A to the 4 we can take from here, and again times 3. So what is 4 times, and now start waking up. Now it's getting really a little bit exciting. What is 4 times 3? Anybody? Second grade, right? It's 12. Modulo 11 is 1. Okay, it's another number. Now stay with me. What's going to, everybody awake? One person doing Facebook, that's okay. So, okay, what's 8 to the 6th? Well, you take 8 to the 5th times a. Well, 8 to the 5th was 1, right? So with 1 times 3 is 3 is 3. Okay. Okay. Let's continue. What is 8 times 7? This is 8 to the 6th times a. 3 times 3 is equal to 9. Okay. Am I right? Yeah. So, what's happening here? I mean, I could continue here, right? I mean, we have 45 minutes. What's happening here? What's happening here? Yeah. Yeah. It's repeating. And why was the 1 so exciting? If you have a 1 here, you're back to the 3 at this point, right? But we had the 3 here. So what happens is we're repeating. You know, after the 1 comes the 3 again, and then the 9 and the 5, right? And here we go down again, right? So the whole thing forms a, English Leistungskurs forms a circle. What is this chapter called? Oh, cyclic groups. Very important notion. Making that a little goofy. This is very important in cryptography. The cycling around. Okay. So what is that? I don't know. I'm pretty good with mental arithmetic. I'm not that good, okay? So, but what do we know? What are the possible outcomes here of this exponentiation here? I made up this number, okay? This is just a random, whatever, 12-digit number here. What are the possible results that can come here? Exactly. There are only 5 possible answers, namely, yeah? 3, 9, 5, 4 and 1. These are the possible answers here, okay? That means you're only touching 3, 4, 5, 9, and 1 if you keep doing exponentiation. Maybe a little bit motivation, why exponentiation? Diffie Hellman, this is really cool protocol from your web browser. What do we do? Exponentiation, 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 all right? So this is, there is some relationship to cryptography, yeah. Nö. Als Hochzahl. Yeah. Yeah. But it doesn't. So he's wondering what happens if we do. Well, you can continue. So the 8 is 9, die 5, yeah? Is this okay? Yeah. Ja, Geduld, junger Mann. Okay, 4. A hoch 10 ist 1. So, was ist A hoch 11? Meinen Sie irgendwie, dass sich das aufhebt, weil den Exponenten, den dürfen Sie nicht modulo nehmen, den Exponenten per se. Okay, ich glaube, das irritiert Sie, ja. That was a good question. So, with this mod 11 does not apply to the exponent. The exponent is not really like a number in the set. I mean, it just tells you how often you have to multiply. That's a good remark, good observation. Okay, so it's important. Now it's getting more and more kind of, I don't know, cooler, but complicated or important or non-trivial. So with the A, with a equals 3, if you look at the all the powers of 3, we can only reach 5 numbers, right? 1, 3, 4, 5, and 9. And this property of the number 3 has a special name. This is called the order, the Ordnung of 3. The order of 3 has the value 5, okay? Which has nothing to do with this 5 that's in the set here. This only has to do with the fact that we reach 1, 2, 3, 4, 5, right? That's the cycle length. Die Zykluslänge is 5. Okay? Okay, everybody is really excited. Let's do another experiment. Let's do the same thing again. Experiment number 3, and I think that's the last experiment for today. Yeah, it's the last experiment for today. So, because we really liked that, we're doing the same thing again. We're looking at the 11 star, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now we're interested in order of 2 is equal to what? Before we figured out the order of 3, now we're looking at the order. And I'm going to give you a definition of the order in a minute. So how do we do that? Well, we did the same thing we did here. We look at all the powers, and we're looking for the cycle length. When does 2 to the something, 2 to the 2, 2 to the 3, 2 to the 4, and so forth, when does this start repeating? So we look at A, I call it A here. A is 2. A quadrat is A square is 4. Oh, by the way, the next 5 minutes are probably the most important part of this lecture here, because the element 2 is special. The element 2 is something like alpha here, yeah? In Diffie Hellman, so that's an important thing. A to the 4 is 2 times 8 is 16. 16 modulo 11 is 5. Very good. 8 to the 5th is 2 times 5 is 10. It's unchanged. We don't have to model reduce. 8 to the 6th is 2 times 8 to the 5th is 20. What is 20 modulo 11? 9. Very good. 8 to the 7 is 2 times 8 to the 6. So 2 times 9 is 18. 18 modulo 11 is 7. Very good. Good teamwork. 8 to the 8th is 2 times 8 to the 7 is 2 times 7 is 14. 14 modulo 11 is very good. We're getting there. Eight to the 9 is 2 times 8 to the 8th, so this is 6. 8 to the 10th is 2 times 8 to the 9th, is 2 times 6. 2 times 6 is 12. 12 modulo 11 is, aha. And now it's getting boring, because 8 to the 11th, well, it's 2 times 1 is 2. But we had the 2 already here. So what's happening here is now that this does repeat, but here, okay. So, everybody awake? Almost everybody awake. Look at the goofy thing, the lächerliche Sache that I'm doing now. I'm checking off which number we generate. The word the generate will be used more in the next few minutes. Okay, so I have the 2 here, I have the 4 here, I have the 8 here, I have the 5 here, I have the 10 here, I have the 9, the 7, the 3, the 6, and the 1. Okay, so by computing 2 to the something, right, this is all 2 to the e, right? And ei runs through all possible numbers here. I'm generating the entire group. Okay, so 2. First of all, maybe let's write the original. Solves the original problem. What is the order of 2? Was ist die Ordnung von dem Element 2? What is the cycle length? Was ist die Zykluslänge? Ja? 10. Very good. So what we're now doing, now we're going to put that in a very systematic fashion, okay? So the order of an element we encountered twice already, right? Here that we figured out the order of the element 3 is 5, and here the order of the element 2 is 10. So there's a more formal definition, which is definition 823 in our textbook, which is, verbally, umgangssprachlich, what it does. You start with the element, you keep computing all the powers until you hit the 1 for the first time. Okay? And this is what you will find in this definition, 8.23. Here. The order of an element A of a group blah 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 is the smallest positive integer such that A times A times A times A times blah 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 is equal to 1. Why did I write the smallest integer there, the smallest integer k? Where is this 3? Here. Does anyone know why did I write the smallest integer k? Why do I need that? Yeah. This one here? Or? Yeah, exactly. Wenn es nicht der kleinste wäre, wenn es nur sagt, hier 3 to the something, 3 hoch irgendwas ist gleich 1, well, this is given for 5, right? But it's also true for 10, and it's true for 15 and 20, blah, blah, blah. So you wanna look for the point where it repeats for the first time. Similarly, with the example we just did, so what is the smallest integer so that you hit the 1 is 10. Are there other integers? I know 2 to the 10 is equal to 1 in this group, right? Are there other exponents where this is true? Any ideas? I'm not leaving that. Yeah, 20. Any other integers? 30, right? Okay. If you have a multiple of 10 here, right, every 10 times you repeat. Okay, you hit the 1 again. But the order of 2 is not 783,315,670. Even though you have a 1 here, the order is 10. Okay, smallest integer. This is what the definition 8.2.3 says, smallest integer. So now comes the most important definition of the evening, of the morning. I wish it were evening. And I'm going to write that down because this is so fundamental for the lecture. A group which contains an element alpha with maximum order and what do you think is the maximum order? If you have a group, you know, the cycling, what is the maximum length that you can get in a given group G? Yeah. P minus 1, exactly, which is always the number of elements here. You can't have more than here, otherwise you would repeat earlier, right? You can't have a, here we only have 10 elements, you can't have a cycle length of 11, right? If you hit the one earlier, you start repeating earlier. With the maximum order, and the maximum order is order of alpha is equal cardinality of G, Anzahl der Elemente, Kardinalität, it's also a German word. So, and now pay attention, wise words from your professor. A group which contains an element with maximum order. So the only thing we are looking for a given group is there at least one element, mindestens ein Element, which has this order. If this is fulfilled, the group is automatic, is said to be cyclic. That means the only condition for a cyclic group, and cyclic groups are super important. Why? As soon as you give me a cyclic group, I can build a crypto system with that. And this is essentially Diffie-Hellman. We're going to do that next week. The step from here to crypto system is very, very easy. Once you have a cyclic group, you have a crypto system, like Diffie-Hellman type of thing, and many other things you can do. It's said to be cyclic. And now, so for instance, is this a cyclic group here? Did you listen what I told you? Is this a cyclic group? Yeah. Why? Because there is such an element, right? There's an element with maximum order here. And these elements now, they get a special name. Elements with maximum order are called here we should really use quotation marks, are called primitive element or generators. In German primitive Elemente oder Generatoren. Ja. So there are kind of two definitions in this. One definition, really the definition of a cyclic group, and then also more like a naming terminology of specific elements. Okay. A equals 2 is a generator of Z11 star. And why is generator a good name? I think I mentioned that before. Well, if you look at 2 to the I, you let I run, I läuft, right? Exponent, 1, 2, 3, 4, blah, 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 blah. What happens here, you generate the entire group. And this is why 2 is called a generator, which is, by the way, not true here. If we look at A equals 3, and we look at all powers of 3, right? 3 to the 1, 3 to the 2, 3 to the third, and so forth. We only generate the subset of A, or of G, right? And this is why 3 is not a generator, because you can't generate the group with that. Generating means taking the exponents here, right? And by the way, alpha right? By agreements, primitive elements are often called alpha, at least in cryptography. Good. So now, and again, maybe I should write that down, not only say that, yeah. Cyclic groups are the basis of discrete logarithm cryptosystems. Punkt. So now the question is, where do we find cyclic groups? And there comes the next definition handy. Die nächste Definition ist praktisch. Yeah, so that's an easy theorem. For every prime p, das heißt für jede Primzahl, zp Stern und Multiplikation is a finite cyclic group. That means if you give me a prime, you do exactly what we did here. This is a cyclic group. Meaning, how is cyclic group defined? A cyclic group is defined via this primitive element, meaning for every zp star, there must be at least one element, one number, which is this primitive element, right? It turns out many, many, many elements are primitive. And now what we're going to do now, we're going to talk a little bit about important properties of cyclic groups. It's almost chapter 4, but it's so let A be an element in G. Also A ist ein Gruppenelement in G, and surprise, surprise, G is a cyclic group. And then we have the following two properties. Erstens, when you raise an element A to the G's power, so G bar, hier mit den Strichen, this is just a plain old integer. This is the number of elements, right? It's die Kardinalität, die Größe der Gruppe, Anzahl der Elemente. So this is always, and this is somewhat surprising, equals to 1, to the neutral element. For every cyclic group that holds. And as always in this course, without proof, you're going to have cyclic groups next year in discrete mathematics, and I'm almost certain my colleague in the math department is going to prove this stuff here. This is basic number theory. Maybe more important, no, not more, equally, they're both important properties for practice here. The order of A, das heißt die Ordnung, for any elements, we talk about any elements, they can't take any orders. If you look at that, we have two examples. Well, one was a primitive element, so that at order 10, and then we had another element that at order 5. So from what we did so far, we might assume, let's pick another element. This was 2, 3, let's pick element 4, and you might get an order of 7 out, and this is not true. Cyclic groups have a lot of structure, and not all orders are possible. Namely, the order of A must divide G, cardinality of G. Okay, for property 1, did Dr. Dürmuth do in the Übung, did he do Fermatsche Theorem? Kleine Fermat? Yeah. So you did Fermat's theorem. I thought you did. Okay. Fermat's little theorem for that P, what Fermat theorem does is, Fermatsche Theorem sagt, A to the P is equal to A kleine Fermat, little Fermat. Okay? But from this it follows, if you divide by A on both sides, you have A to the P minus 1 is equal to 1, but what is the group cardinality? That means how many elements are in this beast. And I think I did that somewhere, right? Didn't I do that today? No, I didn't. We can do that, well, here, right? ZP. So which elements are in ZP star? Well, all elements except the 0, right? 1, 2, 3, 4, P minus 1. So meaning AP minus 1 is equal to A group cardinality is equal to 1. So what I just did, I proved this property. Proof of property 1 for the special case that G here is ZP, that we have these prime groups. There are many other cyclic groups, like elliptic curve groups or hyperelliptic curves or abelian varieties. There are many other cyclic groups, but for us in crypto, this group is particularly important. And here I showed, well, this is true. This some kind of weird behavior is true. And it's easy to prove if you have Fermat's little theorem here. Okay? And now we have to have, in theory, we should prove Fermat's theorem, which we're not doing here at this moment. So now we're going to property 2. And here I'm not going to prove that, but I'm going to give you to look at some examples. Okay? Let's look. Namely, Z11 Stern. And then property 2 only talks about the cardinality, right? It doesn't. Yeah, it doesn't talk about like the group structure per se. It only says, this is G bar. It doesn't say anything else. It's just how many elements are in the group. So the only thing we're interested in is this here. Again, we know the cardinality of these prime groups, of the cyclic prime groups, is 10. And now my question is, based on this theorem, this is not. Question: what are the possible element orders in Z11 Stern, Z11 star? So what do we know about the possible orders from property 2? What does property 2 tell us? Must divide the group cardinality, right? Group cardinality is 10, so what are the possible orders? Yeah. 1 is good, right? 1 divides 10. This is often overlooked. Very good. Order 1 is a good one. What are the other orders? Yeah. 2. Is 3 a possible order? No. 5. Very good. Okay. That means if you do this type of goofy experiment, right? You pick an element. Here I picked 3. The other time we picked 2. And you keep computing all the powers, right? We did this with 2 or 3, but there's 4, 5, 6, 7, 8, 9, 10, and 1 left. If you do that, this yellow arrow that you get out, right? The cycle length must be 1, 2, 5, or 10. You will not get a cycle length of 7 out, or 3. And that would be a beautiful homework assignment for you to do that, but we have a little bit mercy. What I'm going to give you is I give you a list of all the elements here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here I give you the order of. Anybody has an idea what the order of 1 is? 1, exactly. 1 to the 1 is 1. So this is order of 2. 10, right? This is the upper blackboard there. What's the order of 3? Very good. People paid attention. And now it's getting hard, right? So order of 4 is also 5. The order of 5 is also, I have to be careful here. So the order of 6 is 10. The order of 7 is 10. The order of 8 is 10, the order of 9 is 5, and the order of 10 is 2. Just as a side remark, how many primitive elements do we have here in this group? Yeah, yeah, sagen Sie. 4, very good. Or generators. Okay. So, and the last thing for today is and the question is, who cares? Why in the world is Professor Parr doing that, right? 8:30 in the morning, he's talking about, not elliptic curves, cyclic groups, right? So why is that? And in particular, what you should really wonder is, I mean, this seems maybe kind of cool, right? But how is that related? And we're going to talk much more about this next week, but I want to give you a hint, okay? Cyclic groups can make nice, in quotation marks, hübsche, nette discrete logarithm problems. What is a discrete logarithm problem? And again, this will be the main part of next week's lecture, but I want to give you a little bit of a hint, ein Hinweis, eine Idee, what this is. So, let's look at Z47. 47 eine Primzahl, 47 is a prime, so a little bit bigger group than this Z11. And now I give you one number. A equals 5 is generator. So it means if you take 5 to the x or 5 to the I, 5 hoch I, whatever you want, 5 hoch Hochzahl, and you let x run, you generate the whole group. 1, 2, 3, 4, 5, up to 46. You know, just in the same fashion as the 2 generates the 11, right? Everybody with me? And now how is that related to crypto and problems? The following. So we know 5 to the x there is some x that gives me any number. Now, what I'm asking you is, there must be an x such that 5 to the x is equal to 41 mod 47. Do people agree on that? If you don't agree on that, you miss the lecture, okay? You wasted 90 minutes this morning. This must be the case because 5 is a generator, and generator means blah, 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 blah. Okay, generates the whole group. So that means we know x in English, right? X exists. X existiert, right? So x exists. Now, what I would like to know from you is, what is x? Yeah, große Kinderaugen, right? This is really hard. This is a hard problem. I can't do that, right? Well, it's on my sheet of paper. This is a hard problem in cryptography, and to give you a little bit an idea, pay attention. What we do here in the Diffie-Hellman, we use this fact because alpha is known to an attacker, right? Is B known to an attacker? Uppercase B. Yeah or no? Why? Well, it's sent over the channel, right? It's a public key, so this is known. So alpha is known, B is known, alpha is a generator, and what is this lowercase b? That's a private key, right? that an attacker probably wants to compute the private key, even if you don't know any details about that, right? So apparently this is a hard problem. Getting this exponent, how do we compute exponent in 9. Klasse, 9th grade? What is the function that gives us an exponent? Which one was? Logarithmus, right? So in order to do that, you have to compute the logarithm of 41, and this is a hard thing. More next week. Thank you very much.